All right, happy, I don't know, 4th, 5th, 6th week of distance learning. Here's the 2019 exam. This is last year. This is number 2. National average on number 2 was 4.7. My students scored a full point higher than that, which is good. Part B on here, I think I took it off of yours. It's electrochem, so we'll worry about it after the exam's over. Hang in there. There's 2 or 3 more weeks. This is the best thing you can do is these free response questions for practice for these things. So this week we'll get into the 2013 exam. They're all long FRQs in the 2013 exam, so there's no short ones, which is good because there's no short ones on your test. So here we go. 2A. It says molecular formulas of the diatomic bromine, chlorine, fluorine, iodine are written below. Circle the formula of the molecule that has the largest bond length. Justify your answer in terms of atomic structure. So which one's biggest is what they're saying. The biggest one there is going to be the iodine because you got to justify it. Because iodine has more energy levels of electrons, so their nuclei are farther apart when they bond. That's what I got. Tell them what radius means, right? It means the distance between their nuclei once they're bonded. So that's 2A. And we're off and running. 2B you can ignore for the time being, although it's a really easy part of the question, unfortunately. And it's worth 2 points. So you're already starting at 8 points if you get them all right after 2B. So here we go. Here's C. It says bromine and chlorine can react to form the compound BrCl. It says the boiling point of pure bromine is 332, whereas the boiling point of bromine with chlorine is 278. Explain the difference in boiling points in terms of intermolecular forces. We've talked about this the last couple weeks. If you've got boiling points, we're talking about intermolecular forces. And so you've got to identify all the intermolecular forces in the things and talk about why there's a difference in boiling point for each substance, right? So bromine, Br2, only has dispersion forces. BrCl has both dispersion and dipole forces. There's the intermolecular forces. That's your first point in there. And then the second point, the dispersion forces in Br and bromine are stronger than both IMFs in BrCl, and therefore bromine has a higher boiling point. That's what it looks like. It's like deja vu. If you've been keeping up with the FRQs, you've seen that answer 3 times in the last 3 weeks, which is awesome. If you see repetition, this is the whole idea. If we start to see repetition in questions, it starts to put us at a huge advantage come actual test time, because we're going to see repetition there as well. That's part C. Then we get to part D. It says the compound BrCl can decompose into bromine and chlorine, represented by an equation. They give us that it's endothermic. That'll probably come into play later. 0.1 mole sample of bromine chloride is placed in a previous evacuated 2-liter container. Temperature, we've got a moles, liters, temperature, calculate the pressure. Look at that. So you're going to calculate pressure before the reaction takes place, even though eventually it's going to find equilibrium. So before equilibrium takes place, what's the pressure? This is a simple little PV equals nRT problem. And so here we go, part D. PV equals nRT. And we want to solve for pressure. It doesn't say what unit. We're going to do our pressure in atmospheres. So pressure times volume. The volume is 2.00 liters. The number of moles, 0.100 moles. Times the R value, 0.0821. Liters, moles, liters, atmospheres, moles times Kelvin. Be careful that unit's on the formula sheet. Times the Kelvin temperature, 298 Kelvin. All the units should match. Moles, moles, Kelvin, Kelvin. Liters, liters. Make sure that's in liters. Don't get caught. And then our pressure will be in atmospheres. And if we plug this guy in, our pressure equals 1.22 atmospheres. That's us. That's part D. You get a point for part D. Then part E, and we saw equilibrium. We now have an initial pressure, right? And here comes part E. Write the expression for the equilibrium constant for the decomposition, and then it's going to tell you determine the K value. So here we go. We got to write the equilibrium expression from this equation. This is a softball. So here we go. K equals products over reactants raised their coefficients. We've got bromine as a gas. Now look at this one's in pressure for our initial pressure. It says KEQ. It doesn't matter. You can do them in concentrations or pressures. I'm going to do mine in pressures. It's going to make my life easier moving forward. So this is going to be bromine. Make sure you parentheses these guys. Bromine times the chlorine pressure, all divided by the BrCl squared. Don't forget to square it. Reactants over products. That should be it on 2E. We get a point, free point. Then letter F says, after the systems reach equilibrium, 42% of the original bromine and chlorine sample has decomposed. Determine the K value for the decomposition reaction. So what we've got is an initial value of pressure, and they want to know what is our K value, which means we need to figure out what are these equilibrium values, right? And we know 42% of the original stuff decomposed when we reach equilibrium. So I'm not exactly sure, but I know I got initials. I'm going to do a Rice table here and see how this thing shakes out. We've got 2 BrCls going to bromine and chlorine. I'm going to do them in pressures. Our initial pressure we just found, 1.22 atmospheres. I'm going to label that one with a unit so I remember that that's pressures and not concentrations. Could you turn them all into concentrations? Sure, you know how many moles are there, but we've already got pressures, and so I'm going to deal with it in pressures. They don't care whether you do it in pressures or molarities here. The other thing is, look at the Kp for the pressures is going to be exactly the same as the Kc for concentrations, because our N value for the number of moles of gas on both sides is exactly the same. And so you'll get the same answer either way. Our initials on the bromine and chlorine are both zeros. And so we need changes. Our change here, are we going to gain or lose on the zero side? We've got to gain over here on the bromine and chlorine side. So we're going to gain X here and gain X here. And we are going to lose from here. Watch your stoichiometry. We're going to lose 2x there. They tell us at equilibrium how much of that bromine with the chlorine decomposed. It says 42% of the original bromine and chlorine has decomposed. So we got to take 42% of it away from 1.22. So I don't care how you do that. You can take your 42% and say 1.22 times the 0.42 and figure out that that much went away. That's fine. You're going to have to subtract that to figure out how much stuff we had at the end. So 1.22 minus that 42% would give me 0.706 there. Good. And so I've got 0.70, it's 708 is actually the pressure that's left at the end of this in atmospheres. So that's what that guy is, right? And so what did we have to lose from there to there? We lost that 0.512, right? That 41% is what disappeared. And so that 0.512 is our 2x. So if we take the 0.512 and divide by 2, that tells us what x equals. So our x, and these guys are both 0 plus x, is going to be 0.256 here and 0.256 there. And so those are our equilibrium values. And then we can solve for K. That's what they want here ultimately, is what is the K, EQ. And so K EQ, or you could put KP, that's fine, is going to be the bromine 0.256 times the 0.256 from the chlorine, all divided by the 0.708 from the bromine with the chlorine, and it gives us a K value of I almost forgot. You gotta square that bottom part, don't forget. There's our squared. Square that bottom part, and we get 0.13-ish for our K value. That's a tough little chunk. 2 points in that thing. That's a tough little piece of that problem there. But there's you a little equilibrium that's not buffer related. That's plenty fair game come test time. Good? And then we're to part G. So part G says calculate the bond energy, BRCL, in kilojoules per mole using delta H for the reaction of 1.6 times 10 to the, 1.6 kilojoules per mole. They gave us that delta H early on in this. Oh, there it is up there. And so they give us for the reaction, they want the bond energy for the bromine with the chlorine. I'm back to this delta H of reaction idea. Delta H for the reaction. There's our reaction is going to equal, this is bond energies, which means it's the only one that's reactants minus products. So it's delta H of broken bonds minus delta H of formed bonds. It's reactants minus products. They gave us this delta H of the reaction. These guys are all in kilojoules per mole, and so the chart is in kilojoules per mole. This guy's kilojoules per mole. We've got 1.6 for the reaction. Kilojoules per mole is going to equal bonds broken. That's the BRCL. How many of them do we have? 2 of them. And so this is 2 of those Br to Cl bonds minus, for our reactants, we've got the bromine to bromine bond plus the chlorine to chlorine bond. That's what our setup looks like. And then we plug values in. That guy's 1.6 kilojoules per mole. It's healthy to know that they're all kilojoules per mole. There's our bromine, 2 bromine to chlorines, minus, and then we got to plug in the numbers they gave us from the chart. So bromine to bromine is 193, plus the chlorine to chlorine is 243. Looks like that. And we got to add these guys. Be careful, you're adding it to both sides. And when we plug this all in, we should get that the bromine to chlorine bond equals 219 kilojoules per mole. A great check for you is that bond energies are always positive. That bond energy has to be positive for each of those bonds because it takes energy to break those bonds apart. Good? And that's it. That's question number 2 on 2019. There's some tricky stuff in there, so go back through there, double check, make sure you're happy with all of it. Units, 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 units. Later.